Good morning. My name is Michael Stanley, and I'll be your moderator this morning. We're pleased to present this next tinyML talk, Positive Unlabeled Learning for tinyML by Kristen Jaskie from Arizona State University. We've got a few housekeeping slides that we need to go through, and then we'll hand it over to Kristen. Here we go. First, I'd like to thank our sponsors. tinyML has a number of very generous sponsors, including ARM, Edge Impulse, Kixo, SenSIP, Reality AI, Maximum Integrated, and Deep Light. Their support makes these lecture series possible. So thank you very much to them. Also, we'd like to remind you that there's another tinyML talk coming up next week by Vijay Reddy. And he's going to be talking about deep learning benchmarks for embedded devices. The webcast start time is 8 a.m. Pacific time. Also, I'd like to thank my fellow members of the local committee here in Phoenix, Dr. Andres Spanias from ASU, Dr. Suryan Jayasuriya, Steve Wally, who's a member of the board of directors at the tinyML Foundation, Margaret Niffen from NXP Semiconductor, and again, thank you all. If you're not aware of it already, I'd like to make you aware of the fact that we have our tinyML Summit coming up in just a couple weeks. This is quite an event, and as you can see, it's grown tremendously in the last 3 years. We started out with 160 attendees back in 2019. 400 last year, and we're expecting over 3,000 this year. So it's really grown tremendously quickly. And excuse me, just a little delay here in keyboard responses. Kristen, can you back up to the previous slide for me? Maybe you can have better luck. Thank you. I wanted to touch on a couple of the things happening at the summit. It's a full 5 days and over 50 presentations. There'll be a number of panel discussions, the tinyML Research Symposium, and a number of awards in the area of tinyML. So if you'd like to register, please do so. It's free, and I think you'll find that it's going to be a fantastic event. And the nice thing about that event, again, we have a number of summit sponsors. I won't be listing them all here. You can see that they've been quite generous, but their sponsorship makes this a free event. So it's a very easy thing for people to sign up for. You don't have to go back to your corporate masters to ask them to allow you to go to this event. You just register online, and it is an online event. With this, I'd like to turn it over to Andres Spanias from ASU. To introduce Kristen.
Good morning. I'm Andres Spanias. I'm a professor at the ASU and also the director of the Sensor Signal Information Processing Center. It's a pleasure to have Kristen today present to us Positive and Unlabeled learning. She graduated from UC San Diego with a master's degree, and consequently, she went on to run her own company and also serve as the computer science chair lady at Glendale Community College. She joined us in 2017 in SenSIP, pursuing her PhD. She's done quite a bit of work here in machine learning in terms of our workforce programs and some of the defense programs that we are running. She's going to talk about positive unlabeled learning, a technique in machine learning that will help deal with confusable sets of data and also potentially reduce complexity in terms of the algorithms. And without further ado, let me turn it to Kristen.
Hello. So today I'm going to be presenting about positive unlabeled learning for tinyML. Now my background really isn't as much in tinyML. It's more in machine learning in general. However, this is an approach, this is a technique that I believe has a lot of promise for tinyML. So I'm going to start by introducing some of the applications I believe will be very useful, some tinyML applications for this. And then I'm going to talk about an algorithm that I believe will be very useful in the embedded domain or in the non-embedded domain. And I'm going to talk about why and how that works, along with some of the results we've had. So to start with, I'm going to define the classification problem. I'm sure most everybody here is familiar with this. The classification problem, we have two sets. This is a binary classification problem. The positive unlabeled learning problem is really a binary classification problem. We have what we call the positive data and the negative data. We have two types of data, and our goal is to define a decision boundary between these two sets of data so that given a new data point, we can identify, does it belong to the positive set or the negative set, right? The problem is that labeling all this data can be very expensive. And in the real world, we often don't have labels. Standard supervised classification requires that we know that all of these data points are positive and all of these data points down here are negative before we can construct this decision boundary. And this is just not always the case in the real world. So under the umbrella of machine learning, there's three general categories. We have supervised learning, unsupervised learning, and reinforcement learning. And under these, we have a number of different types of problems. Now, positive unlabeled learning sort of doesn't fit in any of these directly. Instead, we're going to have to shift these around a little bit and squeeze in a new category that's less commonly discussed, called semi-supervised learning. And semi-supervised learning really fits between supervised learning and unsupervised learning. And semi-supervised learning has semi-supervised classification where some positive labels are known and some negative labels are known. And then we also have a lot of unknown data where we don't know the labels. And that is its own field. Positive unlabeled classification is an even stricter, more limited version of that, where we actually know none of the negative labels. We just know a small set of one set of labels. So from one of the two classes. We call this positive unlabeled because we have some positive labels and a lot of unlabeled data that we want to classify. So we only have some labels from the class of interest. Everything else is unknown. And it turns out this is a very common situation. Here's an illustration of supervised learning where we have the positive and the negative labels, and we want to construct this decision boundary. An equivalent positive unlabeled classification over here, we only have a small number of these positive labels and everything else is unknown. Both the remaining positive labels, these black dots, and all of the negative labels. And you can see this makes this problem much more difficult because the labeled data and the unlabeled data is completely overlapping, non-separable. And in fact, that's one of the characteristics of this type of problem. And that makes it a lot more difficult to construct a decision boundary when in fact we want to find the exact same decision boundary in these two examples. So I want to give you some motivation of the kind of situations this might show up in tinyML scenarios and when this might be useful. It turns out this is very useful in many problems. In non-tinyML situations, this crops up shockingly often. In medical applications, it's very common in disease gene identification. We have diseases such as Alzheimer's that have a genetic component. We'd like to find more genes that influence a disease like Alzheimer's. But we don't know. We don't know that some gene doesn't for sure influence Alzheimer's. So we can't say that this set of genes does not influence Alzheimer's. All we know is that we have a small subset of genes that does. And so we have a small subset that we know does influence Alzheimer's and a large set that doesn't. Positive unlabeled problem. I could go on for a long time on that vein. So let's jump into the tinyML examples. Here's an example that I think wearable sensors are actually a great example of where positive unlabeled could come in very useful for tinyML. So here's an example of a Holter monitor that you wear. You wear it from anywhere from usually 24 hours to up to a week. I've had to wear one for like 5 days before. It was awful. And you wear it, it connects to your, with these like stickers to your skin, and it measures your heart. And what it does is every time you feel a heart arrhythmia, you hit a button. And so you hit a button when you feel something that doesn't feel quite right. And the idea is that's giving data to your cardiologist to let you know when you feel something off. And the idea is your cardiologist then looks at that and tries to determine if there's anything going on. So the events that are tagged by the user, these can be the positive set. So this is the positive data. But just because you didn't feel something doesn't mean an event didn't occur. You could have been asleep. You could have been watching TV and not noticed. You could have been, doing an activity and again, not noticed. So I don't want to claim that the data that you didn't tag didn't have an event. I don't want to say that's negative data. Instead, we're going to say that's unlabeled data, right? So this is going to be positive and unlabeled data rather than positive and negative data. And we'll see later when I get to the results section how significant this difference is, because it turns out to be remarkably important to call this unlabeled data rather than negative data. And what this does is if we look at if we then give this to the doctor, rather than just showing the doctor the 2 spots that the person felt the arrhythmia, this actually finds all other spots that the person may have. It effectively labels the data. It says, here's another location that the person didn't mark it, but that there was an artifact, there was an event, and it's going to label all the times that there weren't events, right? This is going to label all of the data for the doctor. The doctor's then going to be able to go through, and it's going to probably have to confirm it, but this positive unlabeled algorithm is going to label the data for the doctor. Here's another example, early novel disease detection, because we don't know what that's like at all, right? So for example, lung sounds of, disease X, such as we all experienced last year. We have found in recent months, there has been some work with the coronavirus that they have been able to construct apps that listen to a cough and are able to distinguish if somebody has COVID by the sound of their cough, if they are infected with COVID or not infected with COVID, because the sounds of the cough have unique characteristics. Now, when this is very useful for positive unlabeled learning is in a situation where symptoms are poorly understood, tests have a high false negative rate, and labels are rare. So this is particularly useful in a new and emerging disease. So in a situation such as COVID, I think this would have been very useful during COVID, and that I was doing some research to try to apply it to COVID, not particularly to coughs, but to other aspects of COVID. The idea is especially when you have high false negative rate, you don't want to claim that something is a negative, because you don't really know, because if the blood test says negative, you can't trust that. So you want to call that an unlabeled. So if you have cough sounds, if you have blood test results, if you have anything, if the false negative rate is very high, you don't want to trust that. You want to call that an unlabeled instead of a negative. And from that, can you detect additional positives that might be hiding as negatives? So this is another application for positive unlabeled learning. Machine monitoring. This is a big one in manufacturing. This is a big application in many different fields. The idea is we have a machine that sometimes fails or produces a faulty product. And sometimes the defective product in particular can be difficult to detect. So when we detect that a faulty product has been created or that the machine has failed, we can call that a positive, a known positive. We've found a fault. But if we don't detect the fault, but if there still could be a fault, even if we don't detect one, again, we don't want to call that a negative. We want to say that that is an unknown or unlabeled, right? So this becomes, again, the positive unlabeled learning problem, because we don't want to bias our classifier by saying it's not faulty when it potentially could be. So this is another active area of research for positive unlabeled learning, and another one where it can become very useful for a tinyML scenario. Can we predict when the machine or the product will fail? Okay, my last tinyML application to show you guys before we get on to the actual algorithms. And this is a wildlife monitoring situation. So I know in a tinyML environment, we often have limited storage, we often have limited power. And so in a situation like wildlife monitoring, or many different situations, we might want to only store images or data of interest, right? We may not have a large amount of storage space or power. So if, for example, we have, this is a snow leopard, which are highly endangered. If we want to monitor them and put a camera on their collar and only store images when they interact with other snow leopards. But how do we detect if they're interacting with other snow leopards and only take pictures of that scenario? Well, we may have a set of images that maybe an expert or a supervised classification algorithm can go through and identify images of interest that clearly have other snow leopards in them and tag those as positives, positive data. But especially if we have a series of other images or a bunch of other images maybe captured on a single device that has more storage, we don't necessarily want to write everything off as negative. For example, this image actually has a picture of a snow leopard right there. It's poorly hidden, it's poorly visible. It's well hidden, poorly visible, and it blends in very well, and a human or machine classifier might miss it. But again, what we'd like to do is train a classifier to identify it. So we don't want to label this as negative. We would much rather call this as an unlabeled image than a negative image, because ideally we would like to train a classifier to learn to identify this. So we're going to call this image as unlabeled rather than negative. And so again, if we don't recognize, just because we don't recognize something, we don't necessarily want to call it negative. Giving it an unlabeled label, an unlabeled category may allow us to create a better classification in the end. Okay, so these are some of the examples I've come up with for tinyML applications. I'm sure there are a vast variety of other applications. As I said, tinyML is not my main area of focus, so I'm sure I missed many wonderful applications. But these are some examples that I think would be useful. I think it will be especially useful in health monitoring. I think that's going to be one of the big and important applications for positive unlabeled learning. However, let's dive in now to how does this algorithm work? How do we know it's useful? And what's going on with it? So before we talk about specific applications and specific solutions, I'm going to talk about two important assumptions that are used in this field. And the first assumption is partial separability, because this is the kind of data we get. Now, this is two-dimensional data rather than anything more complex. Two-dimensional data, this is what we get in a positive unlabeled scenario. And if you think about it, this data could have come from either one of these two scenarios over here on the left. And it's absolutely impossible for us to know. Given only this data, we don't know if the data is well separable or it's completely inseparable or anything, in between. It's in fact impossible for us to know. So what we're going to assume is the data that we're given has some degree of separability. It's partially separable. So we're going to assume that the region of highest label density is going to consist entirely of positive samples. So we're going to say over here, this has, this has high density of labeled samples. I'm going to assume this area is all positive. So we're going to assume this scenario up here. We have to pick one of these. I'm going to assume that this is actually usable data. And we're going to assume that where the density decreases, say maybe right in here, over here, that this is where we start to overlap. So maybe this oval should be shifted up a little bit, but that this area is where we start to overlap. We're not assuming complete separability by any means. We're just assuming partial separability. At some point, they are separated. Second assumption is called the SCAR assumption, and this is a very important and significant and strong assumption. And there are people in the field who are working to try to get around this because it is a strong assumption. And the idea is if we have, if this is our negative data, and this black and red is our positive data, we're going to assume that our labeled positive data is selected completely at random from our positive data, right? If we have it biased, so for example, if we only select our labeled positive data from a small area or in a biased manner from our positive data, then it's going to be really hard to learn. How are we going to be able to learn that this area over here is positive? Right? Because as far as the computer's going to see, there's going to be no difference between this data and this data. So bias in the labeling process will be learned and incorporated into the model. So this is another assumption. As I said, there are some people working on minimizing this assumption or weakening this assumption. But the work I'm going to show you today does make this assumption. It turns out that while this assumption is strong and not always accurate in real world data, that the results actually are fairly accurate, and it doesn't tend to have as big of an influence as you might think it does, which means given real world data, we still seem to get very good results, even using this strong assumption. Okay, I'm not going to go through all of these. There are many approaches. This has been a type of algorithm. This is a type of problem that's been around for 20 years. It really became popular or started being worked on around the year 2000, and it's become more and more popular. There's lots of people working on it. Many approaches. I'm going to very briefly go over two of the most common general approaches before narrowing down and talking about a particular algorithm that I've been working on and arguing that it's going to be one of the most effective for tinyML. So the two general approaches, this is the older approach called the two-step approach, though some people are still working on it today. We find a bunch of unlabeled samples that we think are pretty far away from the known positives, and we're going to call those negatives. We're then going to learn a decision boundary between the known positives and what we call the probable negatives. And what we're going to get is a bias classifier, generally. So this isn't really a great strategy in general. The more nuanced approach, sometimes called the weighted approach, and that is we're going to assign a set of weights to the unlabeled data that represent a likelihood of belonging to the positive class. And these weights are no longer going to be binary, like in the two-step approach. We're going to learn a classifier from the known positive and the weighted unlabeled samples. And it's going to give us, in general, a better classifier. The problem is calculating these weights, assigning these weights is very difficult. The most effective methods that are used today to do this either use some variant of risk analysis and deep learning or other deep learning technique, or the one I'm going to show you, which actually is a statistical learning method that is very well tuned for a tinyML. And it's actually, it gets as or better results than some of these deep learning techniques, even though it's much faster and much lighter. And that is called a modified logistic regression. Okay, so So a modified logistic.
Kristen, this is Mike. I'd like to jump in with one or two questions that have come up so far. One question here has to do with unlabeled data and false negative or type 2 errors popping up. And I think the point that the viewer is asking is, are those relevant to the discussion here? In other words, false negatives and
Right. So something is showing up as a negative when it really isn't.
yes.
In other words, as long as we call all of these unlabeled, that isn't an issue. So type 2, so those false negatives, that's perfectly captured in this type of a scenario, and handled. I mean, that's sort of that's perfectly dealt with in this.
Fantastic. And one other question, more application related, is the positive unlabeled halter really used by and large for halter data currently in the real world, or do you think that's a direction for future automation?
Future. As far as I know, that is not used. As far as I know, the positive unlabeled problem is not used in pretty much any health sensor application. I believe that it probably should be. I believe that's a big area for future development. I know it is used in genetic research. That's the big area that it is currently being used in. But I think there's a huge opening, a huge area of opportunity in sensor applications for health research or for health monitoring.
Thank you. I'll let you get back to your discussion now.
It looks like there's a couple of questions in the Q&A. I guess you're dealing with that.
Yep.
Okay. So this modified logistic regression, as I said, there's a couple of other solutions that are using some neural network solutions. I'm going to show you this technique that's gotten remarkable results without going into that more of a complex, more of a time-consuming and a route. So this modified logistic regression, to start with, I'm going to do a really quick logistic regression refresher because I found a lot of people, logistic regression isn't one of the most common machine learning algorithms nowadays. People learn support vector machines and random forests or decision trees, and then they move on to deep learning. And so logistic regression is, I think, an underutilized algorithm. Logistic regression produces probabilities of class membership. And so the general intuition is that we're going to look at the probability that different points belong to the red class. So this point right here, the probability that it belongs to the red class should be about 100%, right? How about this point? The probability that it belongs to the red class should be about 0%. And a point right here in the middle, well, the probability that it belongs to the red class should be about 50%, right? So this, hopefully this is, kind of makes sense, the intuition behind the probability of where these points, the probability belonging to the red class. So what we're going to do, logistic regression effectively adds an additional dimension to plot these probabilities. So we're going to plot the probabilities on another axis, in this case, a third axis, that's going to plot the probability of a point at that spot belonging to the red class. And because probabilities go between 0 and 1, this new axis is going to go between 0 and 1. And what this is going to do is it's going to plot what's called the sigmoid or logit function. So this function has this equation down here, 1 over 1 plus an exponential. And it's going to go, it's this S function. It goes between 0 and 1. And then these are these probabilities of belonging to one of the classes. This is what makes this a good binary classifier. And then to turn it into an actual classifier rather than probabilities, we generally create a threshold and draw a threshold level often at 50%, because with probabilities, 50% is usually a good threshold, though this can be adjusted. So this is how logistic regression works. Now, a modified logistic regression is going to work similarly, but I need to do some background math first. I'm not going to get too deep into math, I promise, but I have to do a little bit. So these are some random variables. We're going to talk about X is the sample features. So here in two-dimensional data, you can think of X being the horizontal and vertical coordinates that describe this data point. Y, so this is not X and Y anymore, like you might have done in algebra in school. X, we have the X1 coordinate and the X2 coordinate. Y is now going to be the label. Is it possible? Is it positive or is it negative? So here, Y is going to be negative. Even at the moment, it's unknown, but I know what the true data is here, and I'm going to tell you this Y is negative, this Y is positive. So that's what we actually want to find. That's what gives us a classifier, when I can tell you what the label is. What we actually know is it labeled or not, right? So right now I can tell you this is not labeled, this is labeled. This is not labeled, this is labeled, right? That's what we're given, is it labeled or not? So I'm going to call that S. I'm going to call, is it positive or not? Y. Is it labeled or not? S. And I'm going to give you a little key up here so you can keep remembering what that means. Okay, and it's important to remember that the positive and unlabeled classes are completely non-separable. Okay, so we're going to use what's called a non-traditional classifier to solve this. And the way this works is that we're going to start by trying to learn if a data point is not if it, our goal eventually is to learn if a data point is positive or not, meaning what is the probability a data point is positive given its feature vector. This is our classifier that we want. But we're going to start by creating a classifier to learn if it is labeled or not, which is the probability, is it labeled given X? And this is called a non-traditional classifier because this is very atypical. This is not the way most classifiers work. So here's how we're going to do it. We're going to start by learning this non-traditional classifier from the data. From that, we're going to calculate the percentage of positive samples that are labeled. So if we have 100 positive samples and only 10 of them are labeled positive, then that means our C is going to be 10%. If we have 100 positive samples and 50 of them are labeled, then we have a C of 50%. Now we're going to be able to calculate that from this probability, and I'll show you that in a minute. Given these two things, we can combine them into what's called this non-traditional classifier to get our traditional classifier. Now, this is a really important result that was proved by Alkin and Noto in a fundamental foundational paper on positive unlabeled learning in 2008. So I'll have a citation at the end of the presentation as well. Hurry, running a little short on time. From this is what we want, right? This is our classifier. From this, we can classify new data. And I can also go back and classify the data we started with and effectively label all of the data that was unlabeled to begin with. And that's the real power of positive unlabeled data, is we can get this unlabeled data and we can give it labels. Okay, so I want to go back to this C. C is the percentage of positive data that's labeled positive. So it's effectively the number of labeled positive data over all positive data. So here's an illustration of when C equals 75%, C equals 50%, 25%, 10%, right? This is just a feeling for, or this is the percentage of the labeled positive. Here's a bunch of math you don't want to see. I'm going to leave it up here just for a second so that if people watching the video can come and pause on this. This is the derivation for this find. Again, it's in this paper, so I'm going to move on. Okay, so back to this non-traditional classifier. We have this result. And again, this derivation was on the previous slides, and I'm not going to spend time going over today. But this is a probability, right? The probability that a data point is positive, given that given its features. We want to know, is it the probability of it being positive? Well, probability is going to be between 0 and 1. For this to be between 0 and 1, it means that this non-traditional classifier, this probability, actually has to be less than or equal to C. Remember, C is that percent that's labeled, the percentage of positive samples that's labeled. So this doesn't go between 0 and 1. Right? This goes between 0 and C. So we're going to have this scenario where this non-traditional classifier does not go all the way up to 1. Goes to C, it asymptotes at C. And the intuition behind this is that the probability of being labeled, the probability that this point should be labeled or not, should not be 100%, right? 100% of these are not labeled. Maybe only 50% of these are labeled. Remember, we assumed that the area of highest density is all positive. That was one of our assumptions. But so if all of these are positive, then the probability of being labeled is only going to be, I don't know, 50%, 30% maybe, something along those lines. So this is not going to be 100%. This is going to be like 30 or 50%. Okay, so given that intuition, we have our standard logistic regression, which goes between 0 and 1. Our modified logistic regression is going to have this new variable in the denominator, which is going to keep the asymptote at a lower value. If B is 0, this term falls out, and we have standard logistic regression. We go between 0 and 1. If B were to go to infinity, then this denominator goes to infinity, and we go 1 over infinity goes to 0, right? And so this line here, this asymptote, is going to vary between 0 and 1. Notice if B is negative, B squared is positive. And so this is always going to be between 0 and positive infinity. Okay, so this C line is going to vary. Now, you may be getting a little bit lost in the math. I know there's a lot of math here. I'm trying to minimize as much as I can, but this is really the crux of why this algorithm works. So if you're feeling a little lost, that's okay. We'll get to the results here in a minute. But with this modified logistic regression, we can now model this probability of being labeled effectively. And from this, way we can learn this, we now have two variables. In standard logistic regression, come on, no, go the other direction. We just have this weight, this is a feature vector of weights, and this is what's learned in machine learning. Now we've got two things. We've got our weights, and we have this new B, this B variable. Now often B is used for bias. I actually wasn't thinking clearly. I was thinking what comes before C, because we use B to get C. So what comes before C is B. So it's not bias, but it's a new variable. So now we have these two, this is really a feature vector of variables and a new variable. And we can use stochastic gradient descent or any other kind of learning algorithm and learn those. And then from that, we can calculate C. And that's how I got B, is it comes before C. And that's going to give us this asymptote. From this, we can finally calculate this, our final classifier, right? This is what we wanted all along. We want to be able to label stuff. We want to be able to say, is something positive or negative? So once we have these two things, we can do that. We can come up with our final classifier. Now, more math nobody wants to see, and you feel free to ignore this. We have our modified logistic regression From this is the probability that a sample is labeled given its feature vector. From that, we can calculate the probability a sample is not labeled. And from that, we can calculate the likelihood of a sample, the labeling of a sample given its feature vector. And this, we can do maximum likelihood estimation. And so again, you don't feel like you have to understand any of this math. I don't want to look at this math. The only reason I'm showing you this math is because if we take the partial derivatives of this likelihood with respect to this W vector and this B, this is actually the algorithm that we use to solve the positive unlabeled learning problem. Right here, we get these partial derivatives, which gives us this update rule, which is the algorithm, which is the only reason I'm showing you this awful math. So if we look at this, right here inside this while loop, that's literally exactly what the algorithm is. This is the algorithm for modified logistic regression. We do a little bit of initialization. We go through those steps of repeatedly calculating those partial derivatives and doing an update. And then finally, we can apply the model and do the calculations to get the S, the C, and finally the Y. Now, what's nice is that this is going to have the same time requirements and space requirements as logistic regression, which is a very efficient algorithm. So if we have the dimensionality, I'm going to call N. I'm sticking with these variables because these are what's in the papers I've published and the book I'm writing on it. Even though you know, F might or D might make more sense here, I'm sticking with the bad way I already chose to do it. So we have the dimensions are N, the number of data points are M, and the epochs, I'm going with E. Doing it to convergence, it doesn't work very as well as one would hope because the terms are very small. You can do it to convergence. I found picking a maximum epochs is more effective. And so our time requirements is effectively linear, right? It's the size of our data by the number of epochs. And then our space requirements is just, you know, how big is the data? It has to fit in memory. And that's it. This is a very efficient algorithm. There are also some techniques where you can make this into a stochastic algorithm or a online algorithm, which might also be effective for a tinyML situation dealing with sensor data. I have not personally played with that, but this is considered a very efficient algorithm, at least until you get to the very big data size, right? It doesn't, logistic regression isn't considered an algorithm that scales very well to the big data. So if you start getting many, you know, dozens of gigs of data, it's not going to be the best algorithm. However, in tinyML, I'm assuming we don't get into the massive big data situation. So I'd like to show you some results. I know we're running a little short on time. As I said, I haven't run this personally on tinyML applications. So I'm going to show you some sort of classical results we've gotten on a couple of things we've tested this on. So the first one, first of all, I want to show you, I keep saying that this modified logistic regression is going to better model that probability of being labeled. So this is, I keep saying, I showed those pictures where I said this is going to asymptote at C. Well, here is, in this first illustration, the true C, this was simulated data, the true C was 25%. So it means 25% of the data was labeled and 75% was not labeled. And what I found is using the blue line as a standard logistic regression to try to learn that non-traditional classifier. And the orange line is using the modified logistic regression to try to learn that non-traditional classifier. And you can see that the traditional logistic regression, this blue line, really desperately tried to get to 1. It really couldn't handle the fact that the probability didn't go to 1. Well, this modified logistic regression just did a beautiful job. Over here, same idea, the true C was 75%. This went slightly over. The reasoning for that, it's gonna have a lot of, it's going to depend a lot on the random selection of the labeled points. And so if, depending on if they're randomly a little further from the boundary or a little closer, yes, they're randomly selected, but there's many different possible random orientations. And this was one of them, and it was a little further from the line, but it's still very close. It's going to give us a good estimate of these probabilities, right? And it's certainly doing better than this poor standard logistic regression, which is just really not cutting it. And remember, we're going to use whichever one of these lines to do our true classifier. And so this orange line is going to give us a much better estimate of these probabilities. Okay, so for the MNIST classifier, MNIST handwritten data set, this is a very standard data set, 28 by 28 pixel images of numbers. Because this is a binary classification problem, I'm going to compare the most commonly misclassified combinations, 3s versus 5s, 3s versus 8s, and 5s versus 8s. And I want to explain for a minute how to read one of these. These are a little difficult to read. First of all, I'm using F-score rather than accuracy. And the reason is because often the data is skewed. The positive class is very much smaller than the negative class. And accuracy is not super effective in that situation. Imagine if 99% of the data is negative and only 1% is positive. A classifier that said everything was negative would be 99% accurate, but totally useless. So an F-score is going to do a better job of balancing that and giving you a more useful number. So this is the MNIST. Now the way to read this is this bottom axis are these C values. So what this is saying is that 90% of the positive labels or positive data was labeled. And when 90% of the positive data was labeled, all the algorithms did pretty well, right? When most of the data is labeled, the oracle is the supervised learning. It means it knows all, it sees all, it knows all the labels. It's doing pretty well, right? Oracle knows everything. Naive standard logistic regression means it's going to pretend that the unlabeled data, it's going to pretend that that's all negative. So this is often a common way it's actually done in the real world is, well, we don't know what it is. I'm going to call it negative. Elkin and Noto, this is using standard logistic regression for that non-traditional classifier. And then this is my solution, the modified logistic regression. So they're all going to do really well at 90%. At 50%, when 50% of the data is labeled, the positive data is labeled, you can see the oracle always does well. The modified logistic regression is going to do really well. Standard logistic regression, or the Elkin and Noto, which is using standard logistic regression for that non-traditional classifier. So we're still doing positive unlabeled learning. We're just not using the best classifier here. It's going to do well. And if we pretend those unlabeled data points are all negative, instead of admitting that they're unlabeled, it's not going to do so well. And then what's really interesting is if we get down where only 10% of the data is the positive data is labeled. So we have only a very few data points labeled. So in this MNIST data, we have about 6,000 3s and 6,000 5s. And we're calling, I believe we're calling the 3s positive here. So that's 10%, it's going to be 600 labeled out of 12,000. So pretty much we have 600 positive and 11,400 unknown in this column right here. Right, so only a relatively small percentage are labeled at all. And everything else is considered unknown, we don't know. The standard logistic regression is just going to totally fail. It can't handle that. And the modified logistic regression is going to do pretty damn well. Right? It's not going to do quite as good as if we knew all the labels, but it's going to do remarkably well, given that we only know 600 labels out of 12,000 data points. And what we find is that if we compare this, I was comparing this to this previous algorithm. I have a 61% improvement, or 61% improvement over this previous algorithm. Now I'm not comparing to multiple algorithms here. There are many of these others that are not being compared here. But I was comparing to the one that was most similar to mine. Okay, if we compare 3s versus 8s, we get the same situation. Modified logistic regression does remarkably well, even at very small numbers of known 3s, and at very small numbers of known 5s. Here's another one. This is some research that I was doing last fall into solar array faults. So this is actually sensor data. This is, we wanted to look at solar arrays, and other research has shown that that these solar faults can reduce efficiency by up to almost 30%. And these kinds of faults include soiled solar panel, when they get dirt on them, shading, whether that's trees, buildings, or even just cloud shading. Degradation, so as they get older, they become less effective, short circuit faults, and so on. And so this is a solar data set I used that had 21,000 data points. Each data point was a different moment in time during a like a daytime period, when there's 10 different features, a whole bunch of different solar features that I'm not going to go through. And so what my job is to try to use positive unlabeled learning to say, what if we only knew of a couple of faults? What if, for example, a human went through and labeled a few fault data points? Could we then look at the rest of the sensor data and predict other fault points without having gone through and spent all that time to label them by hand, which is very expensive? And so this is the same kind of an idea. So this is if we're just looking for soil data. So I'm considering everything else, including shaded, including degraded, all of that I'm calling okay. And I'm just looking for soil data. And what this is there's 21,000 points total. There's 4,000 soil data points. And again, my red line is the modified logistic regression. Blue line is supervised learning, where the Oracle knows all and sees all. I threw in key means. So this is the unsupervised. We have no labels at all. And I'm just trying to cluster it and see, cross my fingers, hope for the best. And it did so well that I started getting into like the smaller and smaller percentages, saying, when can this thing break? And what I found was it finally broke at 2%. So when there are only 85 labeled data points out of 21,000, it finally broke. And that's when it dropped. But as little as 171 labeled points, it got almost as good as the Oracle. So I thought that was truly remarkable. And what that means is that the dimensionality, it's 10 dimensions, is really captured well, even with just 171 data points, is really capturing that well. And as we go on, it turns out some of these, the modified logistic regression is actually working better than supervised learning. And this really stumped me for a while. I can tell you, I went back and I questioned, I'm out of time. I questioned myself. It turns out I'm not the only one getting these results. There's some discussion about that by doing it this way, we may be getting rid of some anomalous data that's screwing up the supervised learning. So if you're getting some anomalous data points that are getting missed in the selection of the positives, you can actually get better modified logistic regression results. And I'm almost done. This is degraded. And finally, doing all faults, you can see that again, this is just finding faults with remarkably, instead of trying to label 21,000 data points and create a model, I can get as good a results with just about 85 data points. And that is it. Here's my contact information and references, and I am done. I'm sorry I ran so late.
You're doing fantastic, Kristen. Thank you so much for a fantastic presentation. We do have a couple questions I want to throw at you from the viewers. Shri comments, he says, we often don't know about distributions when we're solving a practical problem with multiple features. The first assumption that you made when you were working in your derivation how would it affect final results, and how would we tackle those?
Well, the first assumption was that there's some level of separability. We don't actually need to know anything about we need to know minimal information about the distributions, right? I don't need to actually know what any of the distributions are. All I need to know is, or assume, is that the dimensionality that my features, my features cover enough dimensionality to somehow pull out what I'm looking for enough to separate it slightly. It doesn't have to be fully separated. It just needs some portion of it needs to be separated. If that's not the case, you're going to get bad results. Unfortunately, in the real world, if nothing's labeled, it's hard to know. So what you're going to do is you're going to get results that then when you try to apply them, you're going to find that they're not effective. So a reasonable step would be, in a real world situation, you assume partial separability, you learn the model, and then you do a kind of sanity check, right? You go back and you look at the results, and you go kind of to maybe the boundary where you're kind of right in between, and you do a couple of checks just to kind of verify the effectiveness of your algorithm. Now, one of the papers I'm in the middle of working on is one of the things that's lacking from this field is a very effective evaluation technique. And so that's one of the areas of research I'm working on right now, is how can you evaluate the effectiveness of your algorithm, which of course is very difficult because you don't have labels. And so the existing techniques are rather lacking. That is an area of current research, and I'm hoping to have a paper out later this year on that, that will hopefully help with that answer. But at the moment, the best thing I can really tell you is that a sanity check after evaluation is probably the most effective way to verify that.
Great, thank you. Next question. Person asked if the lecturer could comment on the main difference or advancement between this material and the one from her later paper titled PV fault detection using a feedback enhanced positive unlabeled learning method.
That paper is where I got a lot of the data in the later results from. In that paper, I added a little bit of extra, I added a feedback enhancement where I did some extra feature engineering. And so actually in that paper, I did get better results than the ones I've shown today, because I was trying to simplify things so I knew I'd be running out of time today. And so I actually have gotten better results than I've shown you here. It's what I've done is I added a feedback loop for feature enhancement.
Fantastic.
And that's not yet published. That is actually the second reference item on this list that's currently showing. I'm hoping to get that published in the next few weeks, actually, or get that submitted.
Okay, we'll take the remaining questions offline. We will be responding to those and posting responses here in the next couple of days. So thank you everybody for participating. And then again, we'd like to take the time to thank our sponsors, ARM, Edge Impulse, Kixo, SenSense, Reality AI, Maxim, DeepLine. Just kind of stepping through their slides. ARM, the software and hardware potentials for tinyML. DeepLine, we use AI to make other AI faster, smaller, and more power efficient. Edge Impulse, tinyML for all developers. Maxim Integrated, implementing AI inferences at over 100 times lower energy. Kixo AutoML, automated machine learning platform that builds tinyML solutions for the edge using sensor data. And my old friends at Reality AI, tools for building real products. And finally, SenSense. They build low power sensing and inference hardware for embedded mobile and edge devices. Reminder, our next tinyML talk is by Vijay Reddy. in 1 week on March 16th. And thank you for attending. We appreciate your participation.